this, like I said, and I'll post it to the world if or to the internet if you want to see it. So 2 homeworks are posted and 1 quiz. So I would encourage you to check that out. Now, the homework, we did 2 examples. The homework that I posted is what we did yesterday. So the first homework is identical to yesterday's examples we did in class. And then the second homework, and these are the new ones, is a writing assignment. So what I wanted to also point out is there are a couple homework problems that we haven't quite talked about yet, or the style one we haven't talked about yet. So I want to mention that before we go any further. So on homework number 8, there are a couple problems that are different from what we've done so far. And so they are about the mean value theorem. So you'll recall, well, maybe you won't recall, I shouldn't say that. But what I said last week, I believe, is that all these theorems that we have that allow us to find maximums and minimums, these theorems are all theoretically derived from one big result, and that is the mean value theorem. So the mean value theorem is sort of this really, really important fundamental theoretical piece of calculus. It really is at the heart of a bunch of stuff we're going to do moving forward, but it also has some practical sort of purposes. And so what we'd like to do is ask you some questions about this. And so I figured that I'd put a couple on the homework. And so now I think we should do, and I feel real like dry today. It's because there's no one here. It saddens me. Where's everybody at? They didn't even jump in on Zoom. Of course, maybe that wasn't clear that I would be on Zoom today. 4 of like 21 are here today. That's not a good percentage. Yeah, I know. Trust me, I didn't either. Dude, I was like uploading grades. By the way, I started uploading your grades, but I didn't finish it yet. I was like, wait, there's this many people in the class because they don't show up. I'm like, all right, sounds good. So anyhow, let me pull this up. So here's a very basic type of example that we can do. I just lost my pen. So let's look at some examples. Now, again, these are problems sort of analogous to when we would do the squeeze theorem. These aren't really like procedural problems. They're more deductive reasoning. They're more try to write up concise argument problems. So let's look at one. So the first one we want to do is we want to say the following. Show that f of x equals 2x to the 5th plus 4x cubed minus 1 has only one x-intercept. So this is a type of problem that is, this is sort of what I would say a simplified version of a more advanced type of problem, where essentially what I'm asking for us to find is to verify that a certain equation has a solution. Now, there's nothing that suggests that the graph of this has to cross the x-axis. Now, you might say, well, that's not true, O'Grady, because I learned in previous classes that this is a this is a fifth degree polynomial. And you might have remembered when you were in algebra class, you used to talk about like end behavior of polynomials and stuff like that. So maybe, just maybe, you're going to say, well, it has at least one x-intercept. And that's fine, but that's not what I'm asking you to do. I'm asking you to verify, show, reason logically that it has only one x-intercept. Not 2, not 3, not 0, but exactly 1. Does everybody understand the question? So this is sort of an exercise in reasoning. So let's think about how we might solve this. So here's one way to solve it. There's more than one way that you can reason this correctly. So here's one solution. First, we'll use the intermediate value theorem. You remember that maybe from chapter 2. To show f of x equals 0 has at least one solution. And then next, use theorems to reason there can't be more than one solution. And so what this does is this shows f of x equals 0 has a unique, that is one and only one solution. So look, most of you probably don't even remember what the intermediate value theorem says, even though we covered it a few weeks back. The intermediate value theorem is that theorem that tells us if we're positive at some point and negative at another, then we have to hit 0 somewhere. But it doesn't tell us where we hit 0, and it also doesn't tell us how many times we hit 0. It just says it happens at least once. And so that's not enough to show that the solution's unique. So what we need to do is we need to use some better reasoning skills, or I shouldn't say better reasoning skills, but more thorough. So once we know that there's at least one solution, and by the way, let me point this out. When I say has x-intercepts, that's the same thing as solving f of x equals 0. We call those roots or zeros. So at first glance, you might think this is an algebra problem because you're saying, well, Grady, why don't we just set it equal to 0 and solve? Well, good luck, because this is a fifth degree polynomial. You know, if this thing doesn't factor, which this thing's not going to, there's no way you can solve this like you did in algebra class. So we have to use some deeper sort of ideas if we want to understand the behavior. Okay, so let's do that. So here's how this argument goes if you want to write it out thoroughly. So I already forget what the heck the function was. What was it? 2 and 4. So since f of x, which is 2x to the fifth plus 4x cubed minus 1, is a polynomial, it is continuous. So that's the first thing. The intermediate value theorem requires a couple things to be true. First off, they're only true when you get to start with a continuous function. So the most important thing for any of this to happen is that your function's continuous. It's also differentiable because it's a polynomial, which is going to be important in a minute or two as well. So next note, what is f of 0? F of 0 is -1, and f of 1 is 5. Now, why am I doing that? And the first question that you might have is, why did I use 0 and why did I use 1? So the way my brain is thinking right there is I'm looking at that function and I'm saying, what happens when I plug in simple things that I can do in my head? The first two numbers that come to mind that I can usually plug into an expression easily, mentally, are 0 and 1. And it just so happened that my first two guesses worked. Now, of course, they worked right now because I chose this problem so that it's not hard to figure it out. Right? So you would imagine that in general, it might not be obvious what points to try. But then, of course, you could also go to a grapher and graph this thing and note that, hey, it looks like it crosses between 0 and 1. But nonetheless, without me even doing that, so what we have then is the intermediate value theorem. Guarantees at least one root, or you could think of that as x-intercept, between 0 and 1. So if we drew a picture of this, which is sometimes nice to do, if I look at a picture, if this is just my x-axis, now I know when I plug in 1, this thing spits out 5. So this is the point 1, 5. And then when I plug in 0, it spits out -1. So without anything else, I do know this. I know that it has to cross somewhere in here. Or maybe it doesn't look like that. Maybe, you know, what I've done hasn't really said anything specifically about how many I have. It could look something like this. So it might look like this, or it might look like, maybe it looks like this. Does that make sense? So in our analysis right there, just using theory of continuous functions, just using a theoretical tool, we can conclude that one of those two or something like that has to happen. Maybe it crosses 5 times instead of 3. So here's our job now. What we found is we found that it crosses at least once. What we'd like to do is verify that it crosses only once. So to logically conclude it crosses exactly once, all we have to do is study the derivative. So why? Well, notice, what is the derivative of this function? Well, if we go back to the function, it was 2x to the 5th plus 4x cubed minus 1. Well, if I take the derivative, I get 10x to the 4th plus 12x squared is the derivative. Now, what is interesting about this function is that this guy is always positive when x is greater than 0 it is always positive when x is less than 0. Why do we care about any of this? Why do we care that the derivative is positive? Well, the big important thing to take from this is it means the following. This means f is increasing. Since the derivative is positive, the function f is increasing on negative infinity to 0 and from 0 to infinity. So using that, we are done. Why are we done? Because if I sketch the graph again real quickly, here's what I know happens. I know this just from calculus. I know that it comes up, it has to come up and hit here at -1. And then I know over here at 1, it has to be up here. So I know that all it can do is this. And so the conclusion is f has only one intercept, or x-intercept. Again, how do we make this conclusion? Well, it's always going up. The only way it has 2 is if it turns around and comes back down. But it can't turn around and come back down. It has to always go up. So again, it can't turn around. It's always going up. So again, this is one way to do this. It's not the only way, but it's one way. Yes.
So how did you get from knowing it's always positive when x is greater than 0 and always, or it's always, also you wrote it, positive. How do you know, how do you get from it's always positive when x is greater than 0 to always negative when x is less than 0?
It's no, it's always positive in both.
Oh, it is.
It's always positive
Oh, well, then that
in positive. And why is that? Because this is a even power. Even power. So this means no matter what I plug into this derivative, it's always positive, which means f is always going up. Now, notice I was very careful. It's not technically going up at 0. It has a little, sort of like a little hump. Right? So if you go to Desmos and graph this, if I were to graph this function, f of x equals, what is this? What was it? 4x to the 5th? No, 2x to the 5th. 2x to the 5th plus 4x cubed minus 1. So if you look at it, it looks kind of like the x cubed function, but it has this little, by the way, as we predicted, there's a root in here, but it has this one little flat spot. But it's going up all the way to here and then all the way to here. Now, that's not the only way we could have reasoned this, by the way. There are other ways we could have reasoned this, but this is one way of doing it. Another way to reason, which if you look for these kinds of things on the internet, you'll see is this thing called a proof by contradiction. So there's this logically one way to assume something, or excuse me, one way to prove something is true is that you assume that it can't be true, and then you'll reason something ridiculous. And I just don't want to get into that right now because most of you have limited, if any, experience with what we call propositional logic. So to me, this is just deductive reasoning. Okay, let's look at another one. So here's another example. So, okay, what kind of example can we do? Well, let's look at this. So this happens in the real world many times. Suppose we have data, right? We have, and when I mean data, maybe I have a pair of data. And I can think of my pair of data as my one, maybe it's months and value of stocks on that given month, or maybe it's day of the year in temperature in Pittsburgh on that day. So we might have data that we can plot, but we might not have, say, a function that gives us that data. Again, think about that. I can plot, every day I can go outside at 8 in the morning and take the temperature. And then I can go home and record it. Maybe I take an Excel sheet and put day 1, day 2, day 3, day 4. And next to that, I might put the temperature. Right there, I'm not describing a function per se. I'm giving you a relationship. Now, maybe there's some function out there that looks like a continuous or differentiable function that agrees at those points, but we don't necessarily have that. So one of the things we could do is we have data. We can assume that there's some function that gives us this data. So, and oftentimes we want to make predictions about it under these assumptions. So assume we have a function defined on the interval -7, 0. That is differentiable. And by the way, if you're differentiable, you're also continuous. And we know a couple things about it. We might know its starting value. We might know that when I plug in -7, it spits out -3. And we might also know how it grows. That is, we know that its derivative might have a certain property. Say that its derivative is never bigger than 2. So the question we might have is we might be asked to do this. Determine the largest possible value of f of 0. So before we do anything, these numbers I chose, -7 and -3 and 0, all the 2, they're just completely arbitrary. I just picked them. But imagine this. Instead of thinking -7, 0, imagine you have starting point and end point. And imagine we're reading a number line left to right. If we know our value at the starting point and we know the rate at which it can grow, or either up or down, then we should be able to predict what's the largest it can be, say, at the end of the year. Does that make sense? If we know how fast you're growing, we should be able to predict at any time in the future how large you can be. Okay, so how can we think about this? Well, we can look at a picture to get some intuition. And all we can do is graph what we know. So here's what we're interested in. We know if this is -7 out here, we know the value of the function is -3. So this is -7, -3. What we'd like to know is what is the maximum value we can be at 0. Perhaps it's up here, like this. Maybe it does something like this. Maybe it goes straight down like this. What we're trying to figure out is what is the largest value. So for example, if this is the point 0, what is the largest value we can be? So how do we handle this? Well, call this point, instead of calling it question mark, what do we usually do? What was one of the great, I just saw this the other day, it made me laugh. One of the greatest inventions humans ever figured out to solve problems. And it's actually true. It'll piss you off, but it's true. If you don't know what something is, call it X and figure it out. Right? Now I'm not going to call it X, but I'll call it B. And I'll show you why in a second. So the question is, how quote unquote large can B be? No, it's actually not, because typically when we have arbitrary intervals, we say A comma B, right? Isn't that we always say? We say A and B. So that's why. So here's a strategy. What we're going to do is we're going to employ our friend, the mean value theorem. We're going to call him up and say, yo, mean value theorem, help us out. So let's state that. So we can use the mean value theorem. So recall, the mean value theorem says that there is a number C, with C being between B and -7, with f prime of C equaling B minus -7. Excuse me, I wrote that wrong. The functions are up top, with f of B minus f evaluated at -7 all over B minus -7. That's what the mean value theorem says. And by the way, let me clarify something here. I wrote something down incorrectly again, and I actually did that by accident. We don't want to know how large B can be. Let's be much more specific. We could write B here, but it's much more clear, I think, if what is B really equal to? It's f of 0, right? And so what we should, if we're going to be clear, we should make this much more clear. I wrote that unclear, and frankly, what I wrote was incorrect. So what we want to know is how large f of B can be. Remember, that's what the problem says. It says, what is the largest value of f of 0? So I keep writing f of B because I'm losing my mind, but this should be f of 0. And so the mean value theorem, we're actually interested in C, is not between 0 and, or -7 and B. That makes no sense. It's less than 0, but greater than -7. And so I just have to switch these B's out for zeros, and then now we're correct. My apologies about that. Now this looks a little overwhelming, but it's actually not, because we know what some of these numbers are. So let's plug these things in on the next page. F prime of C is equal to f of 0. Now, when we f, it's minus f of -7, but that becomes +3. And then downstairs, it was 0 minus -7, but that becomes +7. Or what we can write is, I'm going to rewrite this. I'm going to write this doing some algebra. F of 0 equals 7 times f prime of C minus 3. So you might say, why did you write it like this? Well, what is the number I'm trying to investigate? I'm trying to investigate f of 0, so I'm going to isolate it. Okay, so now we're going to use some reasoning you learned in like an algebra class, but you never thought to use it this way. So we have right now, what we have is we have a balanced scale. F of 0 is on one side, and then I have this expression on the other. And what I want to do is I want to add weight to the other side so that it becomes unbalanced. But I want to know what is the most I can add. So here's the thing. Since f prime of c is less than or equal to 2, we can reason as follows. F of 0 is equal to 7 times f prime of c minus 3. But now we can replace that f prime of c with 2. Because it's bigger than it. Notice I put an inequality down here now. So I replaced, the only thing I moved out is I took this weight off of my scale and I put more weight on it. So now it's no longer equal, but this side weighs more. And of course you could calculate that. This is equal to 11. 14 minus 3 is 11. And so what we've just shown is the following. Thus, the largest value of f of 0 is 11. So you can write it in English like that, or you can always write very concisely in mathematical symbols. Again, this is a problem that most of you have never probably solved things like this before, or thought this to explain things in this way. And look, this is, this is much more an example of what mathematics is than you computing derivatives and stuff. I mean, computing derivatives is just procedural math. This is thinking, this is reasoning. It's two different things. So anyhow, I hope you'll think about this. I don't pretend that it's easy to learn this, so don't get discouraged. Like these examples we did today are pretty heavy. It takes a while to absorb this information, but give it a try. And if you have any questions, please reach out to me. Please don't forget to check Canvas out and start working on that. Email me with questions. Thank you guys very much, and I will see you next week.